Hi, Nicole. This is 3-4, Heisenberg uncertainty principle problem. The wavelength uncertainty is 1 part in 10 billion, and we want to calculate the uncertainty in position if the wavelength is 0.5 nanometers. And to do that, we're going to use this inequality here, the Heisenberg uncertainty principle. The uncertainty in position is the delta x. Using the wavelength, we're going to find the delta p. So delta x, delta p, just copying this equation down, is h bar over 2. Now h bar is just h over 2 pi. So this is going to end up being h bar over 4 pi because of that 2 that was underneath the h bar. Okay. Now, what is this p? If we want to find the delta x, we have to find the delta p, or the uncertainty in momentum. But you know from the de Broglie relation that wavelength equals h over p. So we can just rearrange that. P equals h over lambda. Now, it's very tempting to just say, well, if p equals h over lambda, h is a constant, so there's no delta there, but then delta p equals h over delta lambda. Unfortunately, that is not the case, however, because this is underneath a fraction bar. So since this delta thing is a differential kind of operator, even though it's not an infinitesimal differential, you have to use the quotient rule. I'll show you why in a moment. But this is how you would do it. You would say actually, instead of using the quotient rule, I always like to use the power rule, because I always get the quotient rule mixed about or reversed or something when I try to memorize it. But this is going to give you dp. So we're going to say that this is a function and this is also a function. All right. So dp equals, bring this exponent down, that's the power rule, right? Lambda, and then subtract 1 from there. So that's minus 2, all right? And then if this is a function, if this lambda is a function, then I got to do the chain rule. So d lambda. So I'll just replace the d's with deltas now, since we're talking about a finite measurable change here. Okay, so now I can find what the delta p is. Now delta in this context is the uncertainty, or the error. So the error is plus or minus. So this negative sign is meaningless in this context, because the uncertainty can go both ways. It could go plus this amount or minus this amount. That's the definition of uncertainty. So that means delta p is really equal to this. Right now, why is this correct? How do you know that it is okay to use this calculus power rule, or quotient rule if you prefer, to find this formula for delta p? Here's how you verify that. You go, if I know that p1 equals h over lambda 1. I'm just copying this equation and putting 1s on the variables there. And if I know that p2 equals h over lambda 2, right? Then the delta p, let's say the delta p is equal to p2 minus p1, right? That's what delta usually means, yes? So in other words, we're saying p2 is the maximum p from a measurement, and p1 is the minimum p from a measurement, right? From a measurement of the momentum by measuring the wavelength, right? So then, how do we get delta p in terms of wavelength? Well, we're going to do this. We're going to do this minus this. All right. So delta p equals h over lambda 2 minus h over lambda 1. Now, to subtract these, I'm going to use the least common denominator. So lambda 1 over lambda 1 times this thing. All right. So that gives me lambda 1, lambda 2, minus lambda 2 over lambda 2 times this thing. That gives me lambda 2 over lambda 2, and then just copy the rest of this down. So now I have the same common denominator, and the top of so the bottom is just going to be lambda 1, lambda 2, but the top is going to be lambda 1h minus lambda 2h. But you see, I can factor out an h here. So it's going to be h lambda 1 minus lambda 2. All right. Now, let me get some more room here. Zip. Zip. Okay. So here we have delta p is now equal to this. H times, now what is lambda 1 minus lambda 2? That is the negative of delta lambda. So if we say that, if we let delta lambda equal lambda 2 minus lambda 1, just like we had said previously, delta p is p2 minus p1, then what we have in here is just the negative of delta lambda. So that's just the negative of delta lambda. And then lambda 1 times lambda 2 down here. What is lambda 1 times lambda 2? Well, lambda 1 is the wavelength that you measured. And then lambda 2 is the wavelength that you measured again, where this one was the minimum measurement and this one was the maximum measurement. And the difference between them, delta lambda, that was just the error in your measurement, or the uncertainty. So since the difference between lambda 1 and lambda 2 is just some error or uncertainty, then lambda 1 times lambda 2 is almost equal to just lambda 1 squared, or just lambda 2 squared, either of those squared, because lambda 1 is very close to lambda 2. The only difference being there is some uncertainty, some error. So I'm just going to call this lambda squared down here. And that is the same thing as we got from matching up the deltas with d's in the power rule in my case, or if you prefer the quotient rule, if you do this like that. All right. So this is h delta p equals h delta lambda over lambda squared, just like delta p equals h delta lambda over lambda squared. There's a negative sign here, but remember, delta in this context means an error or an uncertainty, and errors go plus or minus. So we really want the absolute value of this. Okay, so anyways, whether you do it with calculus or with this conceptual kind of subtraction here, you end up with the same formula. And for us, this formula is going to be what was the lambda in part A? The lambda in part A was 0.5 nanometers. Now, just to be kind of consistent with the rest of chemistry, I'm going to use units of meters here. All right, so I'm going to for H, I'm going to be using this number. It's actually going to cancel out later, but I'm going to be using this joules times seconds, and 1 joule is 1 kilogram meter squared per second squared. So a joule is a kilogram meter squared per second squared, so I'm going to be using meters. So that means I'm going to change 0.5 nanometers. I'm getting that from the problem right here. This 0.5 nanometers, I'm going to change that to meters. So 1 nanometer is 1 times 10 to the negative 9th meters. So this is going to be 5 times 10 to the negative 10th meters, right? That's the delta. Oh, no, that's the not the delta. That's the lambda. That's the wavelength. And now, what was the delta lambda? Well, it says here that the delta lambda is 1 part in 10 billion. So that means 1 part in 10 billion of the lambda. So 1 part in 10 billion of the lambda. Okay. So this right here, this equals h times, okay, now this is going to, this here is going to be 10 to the minus 7th times this 10 to the minus 10th. So it's going to be a total of 10 to the minus 17, right? So that's going to be 5 times 10 to the minus 17, that's a 17 there, not an n, that's a 17, meters divided by, and now this is going to be, 25 times 10 to the minus 20. Wow. That's a big number. All right. So that means that this, we can change that to 1. We can change this to 5. And so to divide, you could just do this on your calculator, really. But negative 17 minus negative 20 is positive 3. Right? So this is going to be 1/5 is 0.2. So 0.2 times 10 to the third. And then there's the h here. So times h. And that is really equal to 2 times 10 to the 2h. So that is 200 times h. 1, 2, 3, yeah, 10 to the 2. So that's 200h. That is delta P, 200h. All right, so we're going to go over here back to the original equation there, the Heisenberg uncertainty equation there. And I'm going to solve for delta x times delta P is, delta, well, here, I'll just rewrite this equation. H over 4 pi, and then I'm going to solve for delta x, right? So delta x greater than h over 4 pi delta p. Now, what was that delta p? That delta p was 200h. So 200h. So these h's cancel very nicely. So we end up with delta x is greater than or equal to 1 over 800 pi. So that is the uncertainty in the position, 1 over 800 pi. So what is 1 over 800 pi? Now, yeah, what is 1 over 800 pi anyways? Do we have to know that? I guess you could just do that on your calculator. 1 over 800 over pi. I think I have a pi here somewhere. Constants. Mathematics. Pi. Okay. There it is. So I'm getting 0.0004 meters. So the uncertainty in position is at least 0.0004 meters. So what is that? That is 0.4 millimeters. So that is delta x is greater than or equal to 0.4 millimeters. Or, if you prefer, 400 micrometers. Or, etc. All right, so that's what I'm getting for delta x in part A. Let's do the same thing for part B. Part B, a visible light photon with a wavelength of 500 nanometers. 500 nanometers. All right, so we don't actually need to do the whole thing over again. We're just going to change this number down here to 10 to the negative 7th. That 500 nanometers is 5 times 10 to the negative 7th meters. So everything is going to be the same, except this number here is going to be 14. You know, it's actually always better practice to do the whole problem over again because there's so many numbers and marks here. It's easy to make a mistake. But negative 7 plus 14 is negative 3. So I think I'm going to be a good student, and I'm going to actually do it over again. All right. So delta P is equal to h delta lambda over lambda squared equals h 1. Yep, see, I had to do it over again because I forgot to change the uncertainty. It's 1 in 10 billion of 500 nanometers. I forgot that upstairs. Did you see that I forgot that? Oh, you should have said something. Haha, just kidding. I wouldn't have been able to hear you anyways, right? Okay, so this is squared. So this is 10 to the minus 7 times 10 to the minus 7. So that's 10 to the minus 14. So this is h 5 times 10 to the minus 14. Divided by 25 times another 10 to the minus 14. Whoosh, whoosh. This is 10 to the minus 14, right? Yeah. Okay. So this is going to be 1. This is going to be 5. So this is really just 0.2h. Wow. That's a big difference compared to 200h. All right, so the delta x is greater than or equal to h over 4 pi divided by delta p. So the delta x is greater than or equal to h over 4 pi 0.2h. So the h's cancel, and I got 0.8 down here. So the delta x is greater than or equal to 1 over 0.8 pi. I think it's the same thing except times 10 to the something else. 4 times 10 to the something else. Let's do this. 1 divided by 4 divided by 3.14159 divided by 0.2 is 0.4 meters. Jeez. So the uncertainty is kind of huge compared to the wave. Is greater than or equal to 0.4 meters, which means that it is greater than or equal to, what is 0.4 meters? It's like 40 centimeters. So you don't know where that, you have, that's more than a foot. You have no idea where the photon is. You don't know where that thing is. You just don't know. Okay, so that's what I'm getting for B. Did you get the same thing? Is that what it says in the back of the book for the answer? I hope so. If not, please let me know. I'd be interested to know also. Thank you.